good to go? All right. Just going to wait for these last few stragglers to take their seats. All right. Hello, everyone, and welcome to the first of two press conferences today, Wednesday, January 9th, here at the 233rd meeting of the American Astronomical Society in Seattle. Today's first press conference is on things that go bump in the night sky. I am the AAS Media Fellow, Karen Hensley, and today I am assisted by the AAS Press Officer, Rick Feinberg, over in the corner, who is monitoring the webcast, and also Frank Reddy, who's going to be helping us with the microphone. Please take a moment to silence your cell phones or anything else that might make noise so we don't have any interruptions during our speakers' presentations. If you subscribe to the AAS press list, you should be getting a lot of press releases related to this meeting, to this press conference. And I want to extend a thank you to Leslie Sage at Nature for helping us to coordinate the press releases, which the embargo for which was just lifted a few minutes ago at 10 o'clock. And several of our presenters today are presenting material that has been published in Nature. So I'm going to go over the ground rules briefly for those of you who may not have been to a AAS press conference before. I'm going to give a brief introduction of our panelists first, and we're going to hear from them in order, saving time for Q&A for the end. So please reserve all your questions and applause until after we've heard from all four of our presenters. So, as I said, the topic for our press conference this morning is things that go bump in the night sky. So we're going to be hearing about everything from the mysterious and poorly understood fast radio burst to a pulsar in the close environs of our galactic center. Our first speaker will be Vicki Cassidy from McGill University, followed by Deborah Good from University of British Columbia, and they will be speaking on early science results on fast radio bursts from CHIME. They will be followed by Aaron Perlman from Caltech, who will be speaking about a study of radio pulses from the galactic center magnetar. Our last speaker will be Aaron Killer from the University of Maryland, who will be telling us about mapping the contracting corona in a new black hole transient with NICER. All right, so I'm going to turn things over to our first speaker.
Hopefully this will. Okay, there we go. So hello, I'm here to introduce to you the first results from the CHIME FRB experiment. I'm one of the leaders of the CHIME FRB team, which is quite large. Quite a few of the members of the team are in the audience now. I just want to ask all CHIME members, raise your hand so you can ask questions of those people as well if you're interested. Here's all the CHIME members, and just want to highlight the students and postdocs shown in pink. They're the backbone of our project, and I'm very happy to have PhD student Deborah Good here to represent that group and to provide you with the relevant background. Deborah.
So in order to talk about our results with fast radio burst, we first need to talk about what is a fast radio burst. These are brief millisecond bursts at radio wavelengths. They've primarily been seen at about 1.4 gigahertz, and none have been seen yet below 700 megahertz for this work. So there are about roughly a few dozen that we've seen so far, but we estimate that the rate is actually about 1,000 per second per day at 1.4 gigahertz, meaning that our challenge is much more in seeing the fast radio bursts than whether or not they are existing in the sky at any given time. One of the other things we know about them is that they are not in our galaxy, and we know this because their dispersion measures are much too large to be illuminated.
The measure is in some ways illustrated by this plot here, which is a fast radio burst. On the x-axis is time, the y is frequency, and this dark gray swoop is the actual burst. That light from the fast radio burst left its source at the same time, but as it encountered gas and dust throughout the universe, Different frequencies were slowed down by different amounts, and in the end, we end up seeing this dispersed, smoothed out pattern. Based on looking at the numbers for those dispersion measures, we can say these bursts are extragalactic and probably cosmological. Where they're coming from, their origin is still unknown. We do know one thing, and that is that one FRB part of this work has been observed to repeat, and that rules out cataclysmic models, at least for that source. Because if what was happening was the star was exploding, you would not be able to see that repeatedly. All right, so we have several key questions. This is the newest field. We've only known about fast radio bursts for a little over 10 years. There's still a lot of open questions. Some of them are, what are they? What are the properties of fast radio bursts? Where did they come from? Are there different classes of fast radio bursts? In particular, how common are repeating fast radio bursts? At what frequencies can we observe these bursts? We know we've mostly seen them at 1.4 gigahertz and above. Some have been seen between 700 and 900 megahertz. We haven't yet seen any below 400 megahertz. Exactly why that is. If the bursts are fainter at those frequencies, are they scattered? Is the light scattered away or absorbed? We just don't know yet. One way we can answer a lot of these questions is through CHIME FRB. CHIME is the Canadian Hydrogen Intensity Mapping Experiment. It's a radio telescope located in Penticton, BC, at the Dominion Radio Astrophysical Observatory. It consists of 4 20-meter by 100-meter long cylinders, each of which has 256 dual polarizations, so X direction and Y direction, antennas on each cylinder. Each cylinder has 256 antennas. That gives us a total number of inputs of 256 times 4 times 2 polarizations. Our input data rate ends up being about 13 terabytes per second. We're rapidly able to reduce that, so we never actually have to handle 13 terabytes per second, but this is definitely big data science. This is a transit telescope, and what that means for us is that unlike most radio telescopes, which point at the sky and move around, time stays in one place, and as the Earth rotates, different parts of the sky progressively pass overhead. That means we see the entire sky in a day. At any given moment in time, we're seeing a strip of the sky which is roughly 2 degrees wide and 120 degrees long, and we're seeing it continuously between 400 and 800 megahertz in frequency. Now I'm going to pass things back to Vicki to talk a bit about our results.
Deborah. So the results that we're presenting and are published in Nature today are the first 13 events that we detected during a pre-commissioning phase of the telescope when it was not at design sensitivity, was being tested, was being turned off and on, and yet we detected these 13 events, which you can see they're plots where the dispersion has for each one been removed, so you can see the response over 400 to 800 megahertz in each plot and the sum in the top profile plots. When we discovered these events, we were quite excited because it was immediately apparent that the sources are detectable in the time band, in some cases right down to 400 megahertz, the lowest frequencies to which we're sensitive, with no diminishment of flux in some cases, no scattering, as could have been expected, no absorption. And so immediately this was clear, this is good news for radio telescopes that are sensitive at lower radio frequencies. They have yet to see FRBs, but there's a good chance that they will get to see them. We did not see scattering in some of our events. This is multipath scattering. But in most of our events, we do see scattering. This is an example of a source with the classic long scattering tail due to multipath propagation. If anything, our search code is biased against finding these kinds, and the fact that the majority of our sources is scattered is quite interesting. And our simulations that have been done by our group show that in order to have the majority of FRBs scattered as much as they are in our sample, it tells us something very important about the location of FRBs in their host galaxies. They cannot be in just random locations. They have to be in special locations that have enhanced scattering, and that's an important clue to their environment. Additionally, one of our 13 sources repeats. That makes it the second known repeating fast radio burst. This was very exciting for us. Represents a new opportunity to localize a fast radio burst. Its localization is insufficient to identify a host galaxy, but once you have a repeater, you can go to an interferometer. You can look for counterparts at other wavelengths, and we are in the process of doing that. Additionally, from the dispersion measure, we know the source is considerably closer than the first known repeater. Its dispersion measure is much lower, and we can only provide an upper limit on its distance, but it's at most half of the distance to the first repeater. Additionally, here are these are 5 repeat bursts, again, all from the same position on the sky at the same dispersion measure. They have different structures. They seem to have different frequency responses. That sort of strange structure, multi-components in some cases, is reminiscent of the burst that we have seen in the first repeater, which is interesting. And finally, the fact that 1 out of the 13 initial CHIME FRB events is a repeater suggests that these repeaters are not as rare as we might have thought previously. So in summary, my time is up, but first results, CHIME has detected fast radio bursts down to 400 megahertz, some completely unscattered and bright at the bottom of our band, which is good news for low-frequency surveys. Most are highly scattered, which is an important clue to the environment in which FRBs exist. They must be in special locations. And we have found the second known repeating fast radio burst. It has bursts that are similar to the first repeater, and it's quite closer and suggests that FRBs are not, repeating FRBs are not rare. Thank you very much.
Hi, my name is Aaron Perlman. I'm a PhD student at Caltech. Today I'll be telling you about a radio study of pulses from the Galactic Center Magnetar. And this is work that's being done as part of a program to actually search for new pulsars at the center of the galaxy. And I just want to highlight some of the people I'm working with. Walid Majid is the PI of that project, along with Tom Prince at Caltech. And the details of these results can be found in a recently published paper of ours. So first, I'll tell you about the highlights of what I'm going to show. One important thing that we see from these radio pulses that were detected from the magnetar center of the galaxy is that we can resolve them during almost every rotation. This is very unusual for radio pulsars, where we usually cannot see them in individual rotations because they're far too faint. So to be able to detect these pulsars, you actually have to integrate them, integrate a number of rotations over some observation time in order to actually see the pulsations. Next, we also see that these pulses from the magnetar are comprised of multiple emission components, and these structure in the components and the number of components that you see vary from one rotation to the next. Some of the emission components that we see are stretched or broadened in time on very fast time scales, while others don't show this behavior. I'd argue that this data set is actually giving us a phenomenal look into the kind of variability that you might see in magnetars, or perhaps if some of these processes are due to behavior from media in the inner part of the galaxy, it's giving us clues to what might be going on there. And lastly, I'll show that some of the pulses from the Galactic Center Magnetar show very similar frequency structure to what's been seen from the first repeating fast radio burst 121102. So first, what are magnetars? Well, magnetars are pulsars. Pulsars are rotating dense dead stars. So what happens is these things rotate about the spin axis, and if the magnetic axis is misaligned with that spin axis as they rotate, what you see is a pulse that sweeps across your line of sight as it's beamed towards you. So that's the animation in the bottom right corner where you can see a pulsar spinning about its axis. Magnetars are different than most rotation-powered pulsars in the fact that they're primarily powered by their ultra-strong magnetic fields and the decay of those fields. And they can have magnetic fields that are 1,000 times that of ordinary pulsars. In addition, magnetars rotate much more than 2,600 pulsars known, but only 30 magnetars out of those 2,600 have been discovered. 4 of them are radioactive. So that means that radiomagnetars are exceptionally rare. They comprise 0.1% of the total pulsar population. So here on the left, I'm showing a plot of central 0.5 degree of the galactic center with the known galactic center pulsars overlaid on that map. And there's only 6 galactic center pulsars known. The closest one is the one almost on top of that yellow arrow. That's the galactic center magnetar, which rotates approximately once every 3.8 seconds. The discovery of that magnetar is actually pretty incredible. It wasn't discovered in radio surveys. It was actually serendipitously discovered through an X-ray flare. And it led to sort of a question that still is ongoing, which is why is the only known pulsar in the galactic center that in the immediate vicinity of the black hole an ultra-rare magnetar. So this has been dubbed the so-called missing pulsar problem. And I'd argue that observations of the galactic center magnetar are important because it allows you to probe the galactic center environment, and that gives you insight into maybe other processes that might affect that galactic center pulsars in the future. So one question you may ask is, how do we know there's a supermassive black hole in the center of the galaxy, and why do we want to search the galactic center pulsar as well? Other groups have actually mapped the Keplerian orbits of stars in the inner region of the galaxy, and based upon their orbits, the best evidence from those orbits is that there's a 4 million solar mass black hole at the center of the galaxy. And the important point is that if you were able to find a stable pulsar very close to that black hole, then you can actually use it to do fundamental tests of gravity and other physics in a very new, ultra-strong regime of gravity that hasn't been probed before. So pulsars are excellent astrophysical clocks, and it's sort of like if you find a pulsar very close to the black hole, it's like having a very precise clock that allows you to probe sort of the gravitational effects of the black hole. So the observations I'll be talking about were recorded with the Deep Space Network 70-meter antenna in Canberra, Australia. We observed the galactic center magnetar over a 1-year period. But today I'll just be focusing on one observation, which is our brightest observation, which is shown on the left here. So in the bottom panel, there's dark speckles. They're actually the relative brightness of single pulsars as they occur during each rotation. And in the top panel, that's actually integrating all those single pulses together to get what's called an average pulse profile. Now, here are some examples of pulses that we detected on individual rotations. And again, we see very significant pulses during almost every time the star rotates. Some of those characteristics include multiple emission components that change from one rotation to the next. And also discussed about how those changes between the separation of the components, they change on roughly tens of milliseconds to 50 millisecond time scales. And the structure of those components can be very different. And I'll talk a little bit about the structure in just a moment. So, for example, in the top panel and in the middle panel, you'll see that the pulses that were detected from these particular rotations show significant pulse brightness. And you see that in some cases in just one component, and then it completely vanishes in the next component just a few milliseconds later or so. So there's a few explanations that we offer, but we're not quite sure what's happening here. One possibility is that if you have some very ultra-dense plasma point that was very close to the magnetar and across your line of sight at high speed, then you could perhaps get broadening behavior and perhaps then not see it in another component. Another possibility is that magnetar pulses are comprised of multiple psychic peaks, and maybe these are just coincidentally a series of those psychic peaks oriented in such a way that you get the observed broadening behavior structure. So another interesting behavior that we saw from magnetar pulses is that in some of those pulses and some of the components, we actually see frequency structure on the same order as what's observed in the repeating FRB 121102. So this is a decrease in intensity that's shown on the left in the bottom panel as a function of frequency, and the size of that decrease is roughly 100 megahertz in extent. And this is approximately what's been observed in other pulses from the computing FRB. So one possible explanation, where we're not precisely sure what could be causing this, there's a few possibilities. One is that perhaps there's some type of plasma lensing going on, and this could be due to the magnetized location in the inner part of the galaxy. Another possibility is this could be something intrinsic to the magnetar, like perfectly usual for magnetars, but we're still trying to understand what's actually going on. One important difference, which has been mentioned in the previous talk, is that FRBs are extragalactic, so they're much further away. In fact, the repeating FRB is 2.8 billion light years away compared to the galactic center magnetar, which is only 27,000 light years away. So that change in distance actually amounts to an energetic burst from the repeating FRB that's more than 10 orders of magnitude greater, which is very important. So I just want to make a remark that you shouldn't go away thinking that magnetars near black holes are the progenitors of FRBs. That's not what we're saying here. We're saying that they have similarities, but we really need more observations to confirm if there's any link at all. And I'll leave you with one final slide for some enjoyment. So what I've done is I've taken a series of consecutive pulses basically added down to the pulses as they come in, and they're recorded by our telescope. And you can actually hear the increase in the structure of the pulse auditorily when the movie plays, so I'll just leave you with that. Pretty remarkable. Thank you for your attention.
Good morning. My name is Erin Clara. I'm an astrophysicist at the University of Maryland and NASA's Adams Space Flight Center. Today I'm going to tell you about a new black hole that was recently discovered. It went from being something totally unobservable to being one of the brightest sources in the X-ray sky on timescales of just a few days. We were able to observe this with the Mensa Observatory, and I'm going to show you a little bit about this result. So black holes exist in our Milky Way galaxy. There are many millions of black holes that exist in our galaxy, and we don't know where all of these black holes are. We can only really see them when they happen to be in a binary system with a star, like a star like our sun, as you see in this slide of this artist's interpretation. So sometimes these binary systems can get so close to each other, the black holes start pulling material off of the star. It can form an accretion disk of material, stellar material around that black hole. And sometimes we see that there can be some kind of instability in that accretion disk that causes this flood of material to rush towards the black hole. When we see this in X-rays, it produces an incredible amount of X-ray emission. It also can launch relativistic jets, as you see in this movie. And in addition to relativistic jets, it also produces what we call this X-ray corona. And you can see that if you can zoom into the innermost regions, at the base of that relativistic jet is where we think this corona is. And the corona is the top of my talk today. So a little bit more about the accretion disk structure. This is now a cross-section of the accretion disk, rotating accretion disk. There's this flood of material towards the black hole suddenly, and we see two primary components in the X-ray spectrum. we see an accretion disk that's about 10 million degrees Celsius, and it emits a low-energy X-ray emission. And we also see high-energy emission coming from a region of very hot electrons and protons and positrons that we call the X-ray corona, and it's about 1 billion degrees. So copious amounts of X-ray emission are produced through this corona, and yet we don't know a lot about what this corona is. How is it so hot in the first place? What keeps it hot over time? And how does it evolve during this outburst? So we see these outbursts. They can last maybe several weeks to months. And there's been a lot of debate in the community. You know, at early times when they emerge from quiescence, they show a lot of strong, high-energy X-ray emission from the corona. And at late times, near the end of the outburst, we see that instead there's been a transition, that the emission from the accretion disk begins to dominate the emission that we see. And how this transition occurs from coronal-dominated to accretion disk-dominated states has been a long-standing debate in the field. As the accretion disk moves in over time, over these several months, and kind of quenches the emission from the corona, or is it something intrinsic in the corona itself that causes it to shrink over time? So we were very fortunate in a couple of ways. On March 11, 2018, the International Space Station was a very busy place. We saw a new black hole transient emerge from outburst, and this was picked up by MAXI. It's an all-sky monitor in the International Space Station, and it's underneath that panel in this picture here. And MAXI is an all-sky monitor with a large field of view, so though we didn't know where this black hole was or even existed in the first place, because of its large field of view, it was able to pick up this incredibly bright burst. And NICER, the other instrument that you see there, was able to flew very quickly to the outburst and observed it basically every day for the next several months. So a little bit more about NICER. This is the Neutron Star Interior Composition Explorer. It's up there on the International Space Station. It's NASA's newest X-ray telescope. And it's about the size of a washing machine, so it's not very big, but it's just incredibly important for studying these very bright objects. So what did we actually find? This is back to this cross-section where you see the accretion disk and the corona is perpendicular to that. We see flashes from this corona. The corona kind of emits in all directions. Some of those high-energy X-ray photons come to us directly, and some of those photons are directed towards the accretion disk, as you can see by those arrows in the schematic. So the radiation of the accretion disk causes it to heat up again, and so you see some time delay, this reprocess emission off of the accretion disk. That time delay is due to the light travel time between the X-ray corona and the accretion disk. And so by measuring these time delays, we can basically map out what it looks like around this black hole system. So similar to how bats use echolocation to map out a dark cave that you can't see, we are using these light echoes, measuring these light echoes to put constraints on what it must look like around this black hole that we cannot resolve spatially with our telescope. So what NICER was able to find, because it has this incredibly fast high time resolution, was that we were able to measure these shorter light echoes than had ever been seen before in a stellar mass black hole system. And that means we're probing closer to the black hole with these light echoes than ever before possible. In addition to that, we saw some energy dependence for these reprocessed photons, and that is a huge indicator for the geometry of the accretion disk. So the corona emits in all directions. It irradiates many radii in the accretion disk, but the photons that get directed towards the innermost regions closest to the black hole will be strongly affected by the strong gravitational pull of that black hole. So as those photons off of the accretion disk climb out of that strong potential well close to the black hole, they'll be stretched to longer and longer wavelengths. And that's kind of indicated in this schematic, the dark blue arrows closest to the black hole. As they climb out of that potential well, they become redder over time. And so this is kind of a good indicator of how close the accretion disk gets to the central black hole. And what we noticed from these observations of these light echoes, we started measuring these light echoes. They were already amazing because they were extremely short. But as we watched the system over several weeks, we saw that the light echoes got closer and closer together. That was indicating that something in the system was getting smaller. So either the accretion disk coming inward or the corona shrinking. At the same time, however, we noticed that most gravitationally redshifted emission, the emission coming from the innermost regions, the amount of emission did not change at all. So that suggested to us that the disk itself is close to the central black hole and does not evolve over time. But because the light echoes got shorter and shorter, closer and closer together, that must mean that the corona is shrinking. So we followed this up for several weeks, and we can make an estimate that right now shrinks from something like 100 miles to only 10. The other important thing is that we've also constrained that the corona itself is vertically extended, and that may suggest similarities between this corona, this X-ray-emitting corona, and the large-scale relativistic blasts that produce radio emission. So, in addition to that, the amazing thing about studying stellar mass black holes and these outbursts in stellar mass black holes is that they evolve over timescales of several weeks to months. And they have, you can watch this evolution happening in real time, and we find now that it's the corona that's driving that evolution. Supermassive black holes exist at the centers of all massive galaxies, and they have an important impact on how that massive galaxy evolves. We want to understand how that process happens, how this black hole that's really 1,000 times less massive than the galaxy in which it resides, how it can have this, how material falls in, and then the material falls into the black hole and then produces an incredible amount of energy. How does that process work in detail? If you want to study this evolution in supermassive black holes, the evolution occurs on billions of year timescales. So these stellar mass black holes are a great analog for studying the evolution of the corona and the accretion geometry in real time. So that's all I had, and I just want to thank my co-authors from the NASA Observatory Science Working Group, and in particular Keith Sandra, who's the PI of NASA. Thank you.
All right, it's now time for the question and answer portion of this session. So for those of you in the room, if you have a question, please raise your hand high and wait for Frank to bring you the microphone so that everyone in the room and also everyone watching on the webcast can hear your question. For those of you watching on the webcast offsite, please queue up your questions on the text chat and Rick will read them to us.
Hi, I'm Alan Boyle with Keyphone, and this would be for Victoria or Deborah relating to time. Based on what you've seen during the commissioning phase, are you able to have any estimate of how many FRBs you might be detecting on a regular basis, like how many per week? And anything else you can say about what you expect the operation of the detection is going to be going forward? Thank you.
So for the initial pre-commissioning phase, as I said, the telescope was not in a stable state, and we were really learning how to calibrate it, and we're still in that process. So it's what we can say, and what's in the papers is that things are progressing with no surprises. Certainly FRBs are present in the band, and we expect to be continuing to detect them, and exactly what that rate is we absolutely have to do our due diligence in characterizing the sensitivity and the exposure of the telescope, and that's exactly what we're in the process of doing. So we'll have more information on that hopefully soon.
Steve Marin, freelance for Aaron.
Which Aaron?
Have you been able, or will you be able to determine the orbit of the magnetar and its distance from the black hole?
Yeah, so the distance from the black hole has already been measured. It's about 0.1 parsecs away, or 0.3 light years. So that's already been measured via proper motion measurements.
With Scientific American for Deborah or Victoria. You mentioned that the high scattering means that it must come from a special place within the galaxy that has that's highly scattered. What sort of locations do you think might be like that?
Yeah, so so we're speaking as a population, generally speaking, because some will see it not scattered, but as a population, they must be coming from those kind of environments. And things that come to mind are in the outer realms of supermassive black holes, or in young supernova remnants, for example, perhaps in star formation regions. Those are the sorts of places that we can imagine, but perhaps there are others that we yet to imagine.
Christine William from the Space Telescope Science Institute. My question is for Aaron. I was wondering,
which one?
The individual substructure and the individual pulses that you showed us, is that something that you've seen in other pulsars as well, or is that unique to the galactic central environment?
So other magnetars also show this spiky pulse structure. So having multiple components in a given pulse is not something that's unique to the galactic center magnetar per se. But other features that we see in individual pulses and those changes, I'm unaware of some of that behavior being seen in other magnetars before.
I think for Aaron and Victoria, so is there anything in the environment of a supermassive black hole that would either switch a magnetar pulsar like this on and off, or cause precession, so that would explain why this seems as random radio bursts? And I know I'm projecting in the future, but I'm just wondering, are we getting closer to an idea of a mechanism here that's connected?
Maybe I can say something first. So for the repeating FRB, one of the characteristics is that sometimes you see lots of pulses in a very short duration, and other times you can look at it for hours and you don't see it at all. So one of the possible theories that has been proposed is that this lensing behavior basically boosts the intensity of those pulses. So basically as the radio beam comes towards you and encounters some type of plasma lens, then you can get very strong magnification of many orders of magnitude, and then you can see it for a very short duration. So perhaps, we're not quite sure, but perhaps one possibility is that these plasma lenses could be in some type of exotic environment such as the galactic center.
I can just add to that it's also true that the first repeater is in a dwarf galaxy and not in the center of the dwarf galaxy. So that's a little puzzling if you want to associate it with a supermassive black hole. It doesn't rule it out. It's not impossible, but that would, you have to answer that question. Why there?
Okay. Eva Simon, freelance. Question for Aaron Keller. Did you also look at what happened when the star releases its material to the black hole? And does it matter what kind of star it is for how the black hole behaves?
The amount of
year. So it's not going to make a huge dent in the star, this star itself. But, in this particular system, it was an M-type star, but you can have much more massive stars, and then actually these winds, you can have a lot of material kind of falling onto the black hole from this, we call this a wind-fed system, and that can change how the system evolves over time.
Carolyn Peterson, Loch Ness Productions and .com. Aaron Perlman, you indicated that maybe some magnetar mystery. Yeah. You said you're sort of talking about some possibilities. What are some of the possibilities of what explaining it?
Sure. So one of the very commonly believed understandings or theories, if you will, is that there is some type of hyperstrong scattering going on at the galactic center. And the effect of that is basically that if there was a pulsar there, then those pulsations will get broadened, and then basically that would be undetectable at lower frequencies. So that broadening behavior has a very strong frequency dependence. So it goes as u to the -4. So one thing you can do is go to higher frequencies to sort of search for these objects, but the problem is when you go to higher frequencies, now the field of view gets much more narrow. Also at higher frequencies, the radio spectrum of pulsars in general is steep, so they're not as bright at higher frequencies, so it becomes more of a challenge.
It's not that they don't exist.
Yeah, right. So they're thought to exist. In fact, there's been observed to be an excess of gamma ray emission towards the center of the galaxy. And that's been proposed to be linked to perhaps an undetected population of millisecond pulsars.
Yes, we have a question from Monica Young at Sky and Telescope. The question for Vicki and Deborah probably, and Andrew may want to weigh in too. The question is, to the repeating FRBs, and I guess she's referring to the new one especially, but also the original one, show significant changes in their individual pulses in the same way that the galactic center magnetar does.
So I'm not necessarily comfortable comparing the galactic center magnetar, but I will say that both the original FRB or repeating FRB and our new one show significant differences in their pulse profile from pulse to pulse. If you remember that plot we showed with the 5, you saw that each of those looked a little bit different, and we know they're the same thing because they're coming from the same location, but they do definitely have different profiles with different bursts, which is similar to what Aaron showed with his sonification graphic. However, I don't know enough about his work to really speculate on specifics.
Yeah, I guess certainly you do see changes from one burst to the next from the repeater. There are some similarities, as I mentioned, with the galactic center magnetar, but again, I'm also a bit uncomfortable comparing a direct relationship between those two classes of objects. It's not yet clear without additional observations if there's any direct link.
And just to emphasize something that Aaron said, is the luminosity difference is many, many orders of magnitude. It's very hard to compare those two.
I actually have a follow-up with the press officer, and I'm not going to force you to compare them as the same object, but I am curious, Aaron Perlman, if you, how eager are you to get your hands on the latest repeating FRB pulses so that you can analyze them in comparison to what you've got yourself?
Yeah, as soon as the press conference is over, I'm getting the paper.
The good news is it's short, we'll still make lunch.
There's one more question here from Shannon Hall. He's a freelancer who's also reporting for Sky and Telescope this week. Question for Vicki Caskey. It sounds like both repeaters' frequencies drift downward over time. What does this tell us about the physics behind these sources?
Yeah, that's a great question. I don't think we know the answer to that yet, but it is striking that they both show that behavior. We have noticed that sort of behavior, qualitatively at least, is also seen in solar type 2, type 3 solar bursts. So that's, again, you sort of comparing two phenomena that so vaguely resemble each other but are totally different energy scales. So the comparison might be superficial and meaningless, but we have noticed you might expect some sort of frequency drifting, as she's noting, due to plasma lensing. On the other hand, both drifting downward, but you would not expect always the same direction of drift in the plasma lensing. But with two sources, I think it's premature to draw the conclusions.
I have a quick question for Tara. As you're watching the corona collapsing and shrinking, are you seeing evidence of the outburst from the accretion disk itself fading in step with that? Are both phenomena sort of petering out together?
Yeah, that's a good question. So there is some fading of the total luminosity of the system, and the spectrum itself suggests that the corona is getting hotter as it contracts. However, there is even, after these observations, we see even a more dramatic drop in the luminosity. Unfortunately, at that time, that's exactly when, your statistics suffer because the source is much lower in brightness, and it's also when the source becomes less highly variable. So it's not really possible to measure these light echoes during that time. But yeah, we can infer that the corona contracts, and it's, in part does drive the luminosity increase, obviously.
Hi, Claire Moskowitz again from Scientific American. And another question for Tara. Do you think that the stellar gas black holes are a good analog for supermassive black holes? But are there any differences besides the mass that you need to take into account to compare them?
Right. That's an excellent question, and it's something that we think a lot about. So there are a lot of similarities in that, supermassive black holes show accretion disks, they show coronae, they show, some of them show relativistic jets, but the density of the accretion disk is vastly different in these two different systems. It's much higher in the stellar mass black holes, and so a lot of the details of the atomic physics don't exactly scale in the same way. But even still, we see the launching of strong outflows in both of these systems, even though they're very different densities and different temperatures. Yeah.
Do you have any more questions in the room or online? Okay. If not, we can end a few minutes early. Let's take a moment to thank our speakers again for the round of applause.
Thank you.
Our next press conference will be here in this room today at 2:15 p.m. and our topic will be black holes and galaxies in the inside. One announcement I have for you is that we will have a press reception tonight at 5:30 in this room, hosted by the National Radio Astronomy Observatory. So I hope to see you all back here either at 2:15 for the press conference or 5:30 for the press